Now, we're going to do a couple of things with charges. First off, I want to put some numbers and some units on things. The unit for charge is the coulomb, okay? That's the basic unit of charge. We spell the word with a little c. We use symbol as a big C. The symbol we use for charges is a Q. We use a little q if it's a little tiny charge. We use a big Q if it's a big charge. And that's it. If you rub an object, it tends to pick up a charge of about a nanocoulomb. Protons and electrons have charge associated with them. This charge right here, 1.6 times 10 to the minus 19th coulombs, is a fundamental charge. You can't have an amount of charge less than that. That's the smallest unit that charge comes in. A proton has that positive charge, and an electron has that negative charge, okay? But that is the fundamental charge. Those will be important numbers for us, and we're going to look at the forces between protons and electrons and such. And so that'll be an important thing for us. Now, if you have charged objects, they exert forces between them. And here's an expression for the force they have between them, okay? It's called Coulomb's law. If I have two charged objects, the force of object 1 on object 2 is equal to the force of object 2 on object 1. Why are those two forces equal? They're equal and opposite forces. That's Newton's laws. So the magnitude has to be the same. They're in opposite directions. The magnitude is this constant k, which is this number right down here, times the magnitude of charge q1 times the magnitude of charge q2 divided by r squared, where r is the distance between them. Does this law look like anything you've seen before? Gravity. It's exactly the same as the law of gravity, except instead of having big G, I've got K. Instead of having a mass, I have a charge, okay? So it's exactly the same form, and it's actually the same form for a very subtle and interesting reason. But these two are the same form as the law of gravity. So the force depends upon the size of the two charges, and it depends on the distance between them. And specifically, as they get farther apart, the force drops off with the square of that distance. That's going to be an important thing for us. Okay, now I want you to try some examples where I want you to think about charges and forces and all that. And we'll start with this one. Got a charged rod that's brought in next to two charged spheres. And then again, a charged rod, which is brought in next to two charged spheres. So the rod comes in, two spheres are touching each other. The spheres are then separated. Then the rod is moved away. So rod's moved in, spheres are touching, spheres are taken apart, rod moves away. When that happens, you might have residual charges that exist on these spheres. These spheres are conducting, so those charges are free to move. Talk to your neighbors about it, and I'm going to call for a vote and say, after the spheres are separated, the rod's taken away, which of these spheres is positive, which is negative, which is neutral? Go ahead and talk to your neighbors about it. I'll call for a vote in 30 seconds. All right, let's take a vote. Which, if any, of the spheres is positively charged once the separation's done? Let's think about that. A and B are together. These are conducting, right? Bring a positively charged rod in here. Where would you expect the negative charges to go on this pair? They go to charge A. Positive charges on B. So this one's negative, this one's positive. I take them apart. Then I move the positively charged rod away. Well, the charges will stay because now they aren't touching each other. There's no way for them to be transferred from one to the other. So when it's all said and done, B is positive, A is negative. How about C and D? Neutral. Because what will happen is the negatives will slosh to this side, the positives slosh to that side. But then when they're taken apart, Both of them has no net charge. It just has a separated charge. Take the rod away, the charges come back together again. And there's no net charge. There's no separation of charge. Let's do another one. This is a picture where you bring a charged rod in next to a conducting rod on an insulating stand. So charges can't move in the stand. They can move in this rod. And there's an uncharged metal ball. So this is a conductor as well, hung from a string. When I bring this rod in next to this metal rod, the ball swings over close to the metal rod, and so it's feeling an attractive force. And you can explain where that attractive force comes from in terms of charges and the motion of charges and the forces between charges. Talk with your neighbors about it. I'm going to call someone's name out of the box and ask the lucky winner to come down and annotate a picture and show where the positive and negative charges are that make this happen. So go ahead and talk to your neighbors. Okay, our lucky winner. Allison, come on down. Oh, and check it out, Allison. Colored pens for you. I got a green pen for the negative charges. I got a red pen for the positive charges.
Okay, so you want me to draw the charges?
I do. I want you to draw the charges.
I think that they're positive charges in here.
It's a metal rod, and so they're free to move, right?
Uh-huh.
So if I take a metal rod, and you're right, initially I'm going to have like positive and negative charges pretty evenly distributed on that metal rod.
Right.
But now I bring negative charges in here. The positive and negative charges say, oh yeah, I'm free to move.
Uh-huh.
The positive charges will feel a force due to these negatives.
Okay.
Are they going to push left or right?
The positive, they're going to go towards it, so left.
So go ahead and draw them.
Oh, okay. So going.
And they don't go all the way. They stay inside the rod. Go ahead and draw them
okay.
inside the rod because they can't come out.
Oh, inside, okay.
Mm-hmm.
So like that.
Excellent.
And
And
then
what happens to the negative charges?
the negative will go towards the ball,
Mm-hmm. Oh, well, they're not going towards the ball. They're going away from
away from the rod.
They're away from the rod. So what you've done is you've made a charge separation. Oh, now, look at this ball. This ball says there's negative charges on this side. So the positive charges move
Towards it,
towards it, and the negative charges move
away.
away. So better put some negative charges in there.
So some negative charges.
Which side will they be on? They're going to be away.
Yeah.
Mhm.
Okay.
And I want to have the same number on that side.
Okay.
Excellent. Well done. Thank you, thank you, Allison.
You're welcome.
Let's have a hand for Allison. Here's what happens. This metal rod gets charged up positive on this side, negative on that side. What's the net charge on the rod? 0. Then this rod has a negative charge on this end. Positives comes toward it. Negatives go away from it. What's the net charge on the ball? How come there's a force on it? There's an induced charge, or there's an induced like charge separation, I guess I would say. Think about this. There's an attractive force between these negatives and those positives, and they're close to each other. There's a repulsive force between these negatives and those negatives. How come that force is smaller than the attractive force between the positives and the negatives? It's farther away, and so that force is smaller. This repulsive force is also smaller. Those are swamped by the attractive force. And so, in fact, you will see an attractive force. You're going to get a chance to see something just like this in the lab this week, actually, with a pie tin. So you'll get a chance to take a look at that.